Okay, hello everyone. Welcome back. Welcome back to Calculus 1000. Today we are going to move to a new section. It's continuation of basically what we started yesterday, the definition of derivative. Now, the goal is to understand how a function cannot be differentiable at a point. So the examples, the facts that we are going to cover today will run around that idea. What are the examples? Why a function cannot be differentiable. Examples of that, and theoretically why it is happening. And at the end, I will pass on the handout that we have for tomorrow. I mentioned yesterday that my assumption is that you guys know the differentiation rules. So we will go a little bit fast on these parts of these sections, but I will give you some handouts so that you see what kind of calculation, or maybe a good review of what you already know. Okay. Before I start, is there any questions, any comments? Okay. Remember that yesterday we said, okay, if you're checking differentiability, which was the idea developed around the tangent line, rate of change, instantaneous rate of change, we are trying to do this limit. F of x minus f of a as x x minus a as x approaches to a. Well, we had an equivalent limit which was f of a plus h minus f at a over h, and h goes to 0. Well, either one of these ones you use at the end, you get the same answer. If the limit exists, we said that this function is differentiable at a, and we wrote it this way. The value of that limit is the derivative of that function at the given point. Well, you guys are coming from another calculus class from high school, so you know tons of differentiation rules. And you may wonder, okay, now that I know differentiation rules, why do I need to know this definition here? Differentiation rules will work in nice cases, but if your function is not one of those nice cases, for example, if it is piecewise defined function, you have no choice than using this definition, okay? And I'll write two examples that I want to start working on. Example one, well, check differentiability of given function at the given point. The first function, which is, maybe you guys like it, you have already seen, but I want you to focus, do the calculation, and what point at 0. The second function is well, I could write this in two forms. I want this function when the power is 1 and when the power is 2. So I will write in general R there. Well, that function is not defined at 0, so I add 0 there. And that's the piecewise defined. In other words, I want this example to be done. First of all, for x0, and we have two functions. When r is 1, when r is 2. But you will see that the calculation will go very similar. That's why I'm putting both of those ones in one example. Okay? I think I will give you 2 minutes. I'm not expecting you to complete both examples. What I'm expecting you is that to start setting up this limit for your function for the given point, and then see if you can evaluate at the end. The same story with this one. Go ahead, 2 minutes. If you're stuck at the beginning, make sure that you talk to the first person next to you. I'm sure that one of you two will know what to do. Go ahead, please.
I think it's a series.
One minute left. You're setting up that quotient and then putting your function in. In other words, as much as you can, evaluate it there. $30 seconds left. Since I don't have enough space there, I will try to write it here. Well, differentiability at 0, no matter what is the function, you have to check this limit, okay? In this specific case, f of x is absolute value of x. F at 0 will be absolute value of 0 over x minus 0 as x goes to 0. But this is the same thing as absolute value of 0 is 0, so I don't have anything in this part, and this will give me that. Okay? Once you plugged in everything and simplify it and get to some clear function that you're trying to find limit, now forget where this function is coming from. This is a limit, yes? I could have given you this limit at the beginning and asked you, what is this limit? Does it exist? What is the value? Well, in this case, when you look at absolute value is a piecewise defined function. When you are for positive values, you get one expression. When you're in negative values, you get another expression. Since we are approaching 0 to 0, that's the point that the domain of absolute value is broken into two pieces. Maybe that's a sign for me to go with one-sided limits. So I will try to then evaluate this with the right limit and the left limit. Okay? Why this is helping me here? Because when you're approaching to 0 from the right, you're working with positive x's. For positive x, absolute value of x is x itself, yes? So then I do have this. Well, this is obviously 0 over 0, and then you need to cancel these ones. You get limit of 1 as x approaches to whatever, that's constant, yes? That's from that point on, you don't need to worry about the value. Here, a negative x, absolute value of negative a number is, I have to multiply another negative sign to make it positive. And, well, the same story goes here. The only difference is that this time when I cancel, I get negative 1. Yes, and limit of negative 1. So right limit, left limit, both exist, but they are not equal. That means that this limit does not exist. But that limit does not exist in terms of differentiability of this function is f is not differentiable at x equal to 0. Yeah? Right limit exists, left limit exists, they are not equal, so the limit does not exist in terms of differentiability, that's what you get. For this other one, I will go with the general R and write, okay, this piece is always there. Now, I want to put the values in. When x approaches to 0, we care about values of x around 0, but not 0. So for all the values of x not 0, the expression is given by this. That means that f at x is going to be x to the power r cosine of 1 over x. And f at 0, well, this definition clearly says when x is equal to 0, you just plug in 0. When x is going to 0. Okay? Or in other words, I have limit of okay, I have x to the power r in the numerator. I have x in the denominator. I can simplify these ones, and I can write x to the power r minus 1. In other words, my limit is x to the power r minus 1 cosine of 1 over x. No matter what is r, this will work, yes? I'm doing just very nice algebraic calculation there for general r. But as I mentioned before, I am specifically interested in when r is 1 and r is 2. So when r is 1, x to the power 1 minus 1, this will disappear here. Then I'll get x to the power 0 cosine of 1 over x as x goes to 0, or in other words, cosine of 1 over x as x goes. When r is 2, this story will be a bit different because now I have x to the power 2 minus 1, which is x to the power 1, cosine of 1 over x as x goes to 0. These are completely two different functions, yes? For r equal 1, you get one function. For r equal to 2, you get another function. Now, I need to check these ones. Do you know what is that limit? Limit of cosine of 1 over x as x approaches to 0. Cosine of 1 over x. Yes, that is the example that we had. It just goes, when we get closer to 0, it oscillates, and you get something like that. So this limit does not exist. And that's an example of a function close to 0. This doesn't have derivative, or it's not differentiable at 0. When r is equal to 2, what about this limit? Limit of x times cosine of 1 over x. Do we have a value for that? Or is it? Yeah, I will need to hear someone.
That's right.
Could you please then ask louder so that everyone can hear what's the question? Yes.
There, for the very bottom equation, were you supposed to write limit as x approaches 0?
Yes, sorry. Yes, thank you. You're right. This x is approaching to 0. Yes, please.
You would probably use like, I think it's squeeze theorem or intermediate values theorem.
Which one? Squeeze theorem. Remember x sine 1 over x? That you will be able to use the same thing. In other words, you can say the cosine of 1 over x is less than -1, bigger than -1, less than 1. Then multiply by x, you get, for positive x's, you get this. For negative x's, you get the other one. But both of these ones tells me that as x approaches around 0, actually in general, this function, our function, is between two other functions, the function x and function negative x. And we know that limit of x as x approaches to 0 and limit of negative x as x approaches to 0, both of them are 0. So our function is between two other functions. As x approaches to 0 from both right and left, squeeze theorem, the bigger and lower function, they have the same limit. Then squeeze theorem will say that these guys push the middle function to have the same limit. In other words, cosine x cosine of 1 over x will have the same limit, or limit 0. Okay? So you see that for r equal to 1, the function here was not differentiable at 0. But when r is 2, this is going to be differentiable. Actually, what you can do, if you're interested, this is something extra. If you can show that if r is 1 or anything less than 1, that same story will happen. If r is bigger than 1, then it will be differentiable and the derivative would be equal to 0. That's a good practice for those who are interested in doing a little bit more challenging work. But it will go very similar to what I have shown on that specific example. Any questions, any comments? This step, setting up this and then putting in what is your function, what is value of the function, should be always the first thing you're doing when you're trying to use the definition of derivative. And then you go from there, you use all the tools you have for the derivatives, and then you try to evaluate them. If you don't have any questions, then I will start another example on the iClicker. Yes, the iClicker. I just posted the question. There is this function, and you're trying to check the differentiability of that function at 0, or the slope of tangent line at x equal to 0. I know that, well, if you click on any of them, I see already some people did, you will get the mark you're looking for, but please make sure you start doing this example as the steps we showed in different, on the steps of different examples. Start with the definition, plug in the function. What was the function? Function is f of x, x times absolute value x plus 2. The point is x equal to 0. Another 30 seconds. Okay, make sure that you're putting your answer in.
You're sitting on the stairs.
And I'm closing it in 10 seconds. Okay. The first step is this, yes? Let's write this, and then limit of f of x is x times absolute value of x plus 2 minus, at 0, it's 0 times absolute value of 0 plus 2 over x minus 0 as x approaches to 0. 2, 0, 2. These two cancel. And here you get just 0, and then the function you're looking for is x, absolute value of x over x. And yes, you try to use quotient law. The limit of the denominator is 0. The limit of numerator is also 0. So you have to factor cancel. Here, well, the terms are clearly there. And you're dealing with limit of absolute value of x as x approaches to 0. What is limit of absolute value of x as x approaches to 0? 0, yes? Look at the graph. You look at the definition. Either way, this will give you 0. So yes, this function is differentiable, and f prime at 0 is indeed 0. Any questions, any comments before I move to another example? Okay. There is the next step for us is to determine how differentiability and continuity are related. To be able to understand that, I'll ask you to work on this one example, which is, okay, I have a function, and I have this limit, f of x minus b over x minus 3 as x approaches to 3 is equal to 10. find limit of the function itself as x approaches to 3. Okay, write it down, this one. I'll give you 1 minute, and I'm not expecting you to write anything on your notes. What you're going to do is that talk to the person sitting next to you, and you're trying to see what is special about this example. What makes it an example? This example interesting. 2, how I can move from that big information given there, that quotient limit, to the limit of only part of this whole thing. And in particular, you are trying to think, what did we do when limit of denominator was 0? Okay? That's a hint. So you're talking to your friend about why this is important, what are the tricks we can get from that big chunk of quotient things into that function f. Go ahead, you don't need to write down anything, but you're discussing with your friend, I need to hear some noise there. Go ahead, please. Ten more seconds, and then I will need volunteers to tell me how. Okay. Okay. Can anyone, okay, at least tell me what is the limit here? Can anyone give me, yes? Is it B? Let me see how many of you say it is B. You're alone there. Sorry. Okay, what else? Do I have any other answer? What is the limit of that function as x approaches to 3? Give me another one. Yes, I will stay here until I hear one more. Go ahead. No other thing? Not even 0? Not even 10? Not even 0? What? Okay. It seems that I'm stuck with you. Okay. Can you tell me what was your approach in what you said?
Okay, so
okay. Louder, please.
First I applied quotient rules, so I got limit of x approaching 3, f of x minus b over lim x approaches 3, x minus 3. And all of that's equal to 10.
Yeah.
So then I took lim x approaches 3 for x minus 3, and I cross multiplied. So 10 times lim of x approaches 3 for x minus 3.
Someone cross multiplied something from inside of limit to the other side, which doesn't have any limit.
So you applied quotient law, and that.
Wait a minute. Can you apply quotient law here? The denominator is 0. Limit of denominator is 0. What would you do then? Check the limit of numerator, yes? if the limit of numerator is not 0, you have a number in the numerator divided by 0, then we wouldn't be able to find the limit value. It would be infinite limit. There would be non-existent limit in that case. So that means the limit of numerator must be equal to 0. Or I will work on the idea that you were saying, which is more mathematically doable. I know that this limit exists I multiply both sides of this equality by limit of x minus 3 as x approaches to 0. Okay? I know it is 0. Well, I multiply two sides of an equality by 0. Yes, a little bit not really feeling good, but I wanted to turn this I wanted to see this as a result of the product law. This limit exists, so limit of the product will be limit of this and that, yes? But here, I can cancel these two, and the right-hand side, this is equal to 0. In other words, we showed that limit of the numerator as x approaches to 3 is equal to 0. Yeah? It's kind of what you were trying to say, but you're jumping mathematical steps, but that's good. Okay? Now, apply difference law, and that will give you limit of f of x as x approaches to 3 minus limit of b as x approaches to 3 equal to 0. But b is a constant, yes? Limit of constant is always that constant, and I take it to the other side. So I get limit of f of x as x approaches to 3 is equal. Why that limit is important for me? Before I say that, is there any question or any comments on what we have written on the board? Any questions, any comments? Well, now, let's say instead of this thing, I have a function which is differentiable. F is differentiable at x equal to a. Means what? Means that this limit of f of x minus f at a over x minus a as x approaches to a exists as equal to L. It's a number. Yeah? Do you see any similarity between this and that? In the denominator, I have x minus a, and x approaches to a. Here I had x minus 3, x approaching to 3. Yes? In the numerator, I have f of x minus a constant b. Doesn't matter what is that constant. In this case, it's f at a, yes? And then, also, we know that this guy has a limit. That one also had a limit. Wait, would this be different if my limit was 100 there instead of 10? It would be the same thing because we will multiply and this will be 0. 1,000 or any number was there. The only thing mattered to us was that limit exists. And now this limit exists as well. So you can play the same game. And you will get limit of the numerator is equal to 0. Or as x approaches to, I'm following exactly same steps. Here, b over there is f at a. Both of them are constants. After you evaluate it, it's constant. Yeah? What does this mean? What does this mean here? Limit of f of x as x approaches to a is f at a. What does it mean? If I don't get an answer for this, I will stay here until the class ends. Or no, how about this? I'll give you 20 seconds. Talk to your friend, check your notes. This is an important condition. Tell me what does that mean? Go ahead. 20 seconds. 20, 19, 18. Check your notes. Talk to a friend. Three, two, one. Okay. What does that condition mean? You didn't find it in your notes? What was it? It's continuous at A. This means that f is continuous at A. This simple example, you can generalize it in general, and you get this very strong fact, which says if f is differentiable, it is continuous at that point. So let me write this as theorem. If f is differentiable at a, then it is continuous at differentiability implies continuity. Remember, the weaker condition was the limit exists. Then we studied continuity. Limit not only exists, but it's equal to the value of the function at that point. Now there is another stronger condition which says differentiability implies all these things happening. Or if I want to put all the functions which have limit at a, will be very large set. The limit exists at a, then a smaller group of that would be continuous at a, and then a smaller group than that would be differentiable. Differentiability is a stronger condition than both continuity and the limit existence. Before we move on, there is a thing here that you have to check. This says that everything which is differentiable will be continuous at given point. Is the opposite of this correct? Is the converse correct? No. What is the example you have for that? Absolute value of x is continuous at 0, but I think it's somewhere here, back here, yes? Or no, it's absolute value of x is continuous at 0, but it is not differentiable at 0. So no, continuity doesn't imply differentiability. The other way around is true. Now, I want to list few cases of why or when a function is not differentiable. When examples of when a function is not differentiable. Since all differentiable functions are continuous, if something is not continuous, we can say that, well, they are not differentiable then, yes? So the first thing is that f is not continuous at the given point. Well, this could mean that the function doesn't have limit. If it doesn't have limit, then it's not continuous and so on. Or it is something like sine over x, cosine over x, oscillates. Or it has limit, but the value of the limit and value of the function are not the same. These are all examples of the functions that are not continuous. Sorry, that are not, well, continuous and hence not differentiable. 2, examples that are continuous but not differentiable. One group of those are the ones that have a sharp turn, or you like to say, what was it? Cake or cusp? Yeah. You again said cake, yes. Cusp points, or the ones that f has, the graph of f has a sharp turn at that point. So something like absolute value of x, or it could be something like that. There is also another interesting case that is continuous. It doesn't have sharp turns, but it's not continuous. And this is when f has vertical tangent line. So in other words, something like that. The function is very nice. Everything works nicely. There's no strange thing happening there. But when you try to find the limit of the slope of the tangent line, you get infinity. And that is when you have vertical tangent line. Example of that, you can check the book. This is done very carefully in the book. The third root of x at 0 is of that form. Tan inverse at 0 is also like that. So they are very good. Everything is nice and clear, but they have vertical tangent line. Any questions? Any comments? This fact here sometimes is going to help us with examples like this. Let me see if I have my example. For what values of a and b, function ax plus 3 for x is bigger than 0, x squared plus x plus b for x is less than 0. Am I doing it right? That's minus. There's only one thing that I have to change there. Okay? This is my function. For what values of a and b, f is differentiable at x equal to 0. Write it down. I don't think I have much time. 4 minutes. Maybe I can give you 1 minute. I can give you 1 minute. No, you don't want that 1 minute. Okay, 1 minute. Try to see if you can apply this fact and what kind of condition you will get from that. Go ahead, please. And you have 1 minute. I won't be able to give you more than 60 seconds. Go ahead, please. You're tired today. Please pass it on. You have 30 seconds left. Oops. Take those. You're checking for what values of a and b. The function will be differentiable at 0. You have 15 seconds left. Oh, I'm sorry. Oh my God. Okay, there will be some extra ones up front. Please, those who don't get anything, just come up front at the end. I'll find someone give you. Okay. So you can try to go ahead and try to find the limit that defines the function, the derivative. In other words, you can do, okay, limit of f of x minus f at 0 over x minus 0 as x approaches to 0 must exist, yes? Here, since these are piecewise defined, I will split to 2 pieces. Limit of x going to 0 plus, limit of x goes to 0 minus. When x approaching to 0 from positive side, my function is ax plus 3 minus, what is f at 0? What is f at 0? You have to plug it into this one, and yes, 0 squared minus 0 plus b. So that's minus b divided by x minus 0. When x approaches to 0 from the left, you have x squared minus x plus b minus b x minus 0. So if you want to go this direction, you will get stuck a little bit. It's not that horrible case, but you can fix that and try to find it. But you can also say that since if f is differentiable at 0, then it must be continuous at 0. Being continuous at 0 means that the limit exists, or in other words, from the left, you get limit of x squared minus x plus b as x goes to 0, which is 0 plus b. On the right, this is 0 plus 3. This must be equal to b. Left limit exists, right limit exists, they're equal to the value of the function. Yes? If you apply that fact, right away you notice that, oh, before when I start doing the differentiability, I can find the value of b. This says that b must be equal to 3. b is equal to 3. Now, I don't need to work with two variables. I just need to work with, I already know b is 3. This will go away. So I have limit of 3 minus 3, they cancel, ax over x. As x goes to 0, these two cancel. That's a. This other one, oh, this is limit of x squared minus x. So I can factor out x over x. These two cancel. You get limit of x minus 1 as x goes to 0. And that is negative 1. Function to be differentiable at 0, not only we need b to be equal to 3, also I need the left limit of this quotient or rate of change be equal to the right limit of that. So in other words, a must be equal to negative 1. See, that fact that differentiability implies continuity can be used in questions like this, and then you get something, some information first before you start even studying the actual limit for the derivative. Have a great day. See you all tomorrow. When you come back tomorrow, we will work on the handouts. If you have handouts, extra handouts on the desk, please bring it up. There were some people who couldn't get enough. So I will bring more tomorrow as well.